When I was asked to do this talk some months ago, I rather grandiosely entitled it From Parasites to Planets. After I finished my exams last week, I started writing my talk, and I thought maybe I should revise it somewhat. 15 minutes is not really enough to do the topic justice. So I'll change it slightly to the pervasiveness of parasites. We've all eaten now, so I can feel I can actually talk about this subject. So to start with, I want to talk about some of the really small impacts of parasites on individual species like humans and insects. And then I'll take a step back and I'll look at the bigger impacts that parasites have that you might not have thought about in everyday life. So the word parasite literally means beside food. And in the first place, it was to refer to people who might be able to get a meal at a nobleman's table in response for doing some sort of act or performing a task. Then it came to mean a character in Greek comedies. So parasites have been known about for a long time. Aristotle observed cysts in the tongues of pigs as hard as hailstones, which when he cut them open were full of small worms. The Egyptians and ancient Chinese had remedies that they used to kill worms in the guts. So some religious texts as well refer to animals to try and help us to avoid parasites. This quote from the Quran: "He has forbidden you dead meat and blood and the flesh of swine." And this one from the Bible: "And the swine, because it divideth the hoof, yet cheweth not the cud, it is unclean to you. Ye shall not eat of their flesh, nor touch their dead carcass." So pigs are a major source of food that infect humans with parasites. And these are religious texts telling us to stay away from these animals. So they were known about, but they weren't particularly well understood. And this was perhaps best exemplified by the attitude of Renaissance and Victorian physicians towards disease and parasites. European physicians believed that diseases were the result of the body being out of balance, or as a result of miasma. Miasma is the Greek word for pollution, and they believed when there was rotting vegetative matter, it would release bad air or dark air, which would make people sick. And they thought malaria, fever in the tropic, was a result of bad air from rotting vegetation. Guinea worms, which live in people's shins and people spool them out gradually with a stick, they believed this was the result of too much acid in the blood, whatever this was. And I found this quote during my research, which I think really exemplifies the attitude of physicians towards diseases. And it's: "From inhaling the odour of beef, the butcher's wife obtains her obesity." So it's not particularly logical. And there was this idea as well that parasites weren't actually the cause of a disease, they were just a symptom. So if someone was diseased because of bad air or their body was out of balance, then these parasites would just come into being spontaneously, this idea of spontaneous generation. And the problem for biblical physicians was that this was heresy, it was deeply heretical. They believed that everything was created at the time of Genesis, and everything was created for a goal, and that's what God intended. So things couldn't just spontaneously generate in our guts, in our blood. And there was a particularly pious doctor called Kutchenmeister who lived on the outskirts of Dresden. And he set about to disprove this theory of spontaneous generation. And he started on small animals, so he started on foxes. And he'd feed them infected pork, and he'd dissect them out, and he'd find juvenile stages of the parasites. And he moved on to other animals, so he moved on to sheep and pigs and cows and goats, I think. But then to really prove it and drive home his point to the scholars of the day, he started to infect humans. And he got permission to infect a prisoner who was to be executed the next day. He went down to his local restaurant and he got some raw pork, out of which he picked some worms. He put it in a warm noodle soup and he gave it to the prisoner. The prisoner liked it so much he asked for seconds. The next day he dissected the prisoner and he found juvenile stages of the parasite. Now this blew the spontaneous generation idea out of the water, and to really prove his point, 5 years later he infected another prisoner 3 months before his execution, and then after his execution cut him open and found some of the adult forms of the parasite inside it. So he managed to prove, right, things were created at Genesis, maybe they came inside us at a different point. The problem with spontaneous generation was no one had actually seen a tapeworm crawl inside someone's mouth. And he had no explanations for how these things got inside our body. So how do they get inside us? There's lots of different ways. Usually it's because we eat them, we don't cook our meat properly, or we've been gardening and we don't wash our hands when we cook food. But some parasites have developed ways that they actually get into our bodies that are really ingenious. And I've picked one in particular, which is parasites of the species Schistosoma. If you've been to the tropics, you probably know what I'm talking about. They have an interesting life cycle where they live in snails and humans. And they'll live near water and they'll crawl out of the snail into the waterway. If it's sunny outside, they have enough of a nervous system that they can detect the sun, and they'll go down into the mud on the bottom of the lake and avoid the UV. But if you or I get in the water, they can detect molecules released from our skin, and they'll swim along this gradient towards us until they come in contact with our skin. And if you feel your skin, it's pretty strong, it's quite impermeable, and you wouldn't think a tiny little parasite would be able to get into it. But this one has a clever way of doing so. It releases a chemical on our skin that softens it until it's about the consistency of mud. At this point, it can swim into the skin until it reaches a capillary, which are quite narrow, so it pulls itself along with specialised suckers. It goes along our venous system until it reaches an area where the blood's strong enough to carry it around our body. All of our blood eventually reaches our lungs, and from our lungs, this parasite will grow down to our liver, where it starts to feed on our blood. At this point, like all animals, they want to have sex, they want to reproduce, and they need a mate to do this. So they release a chemical in our bloodstream which travels through our blood, which will attract a mate of the opposite sex. At this point, like a lock and key, they'll lock together and they'll start breeding, and they'll move from our livers to our large intestine, where they'll attach themselves to the substrate provided by our gut. At this point, they just release lots of eggs, and most of them are excreted, although some go into the liver where they cause lots of pain.
Keep going, I think.
So, I will step back from the repulsive nature in a moment. And this is how they anchor themselves inside us. Don't worry, in New Zealand we don't really have a problem with parasites. But they develop these sort of morphological adaptations, and they need a way to stay put. So in the case of tapeworms, for instance, they're very small when they come in, but they get a lot larger, up to 1.8 million times larger. And your gut's peristalsis are wave-like movements through your digestive tract that would push them out otherwise. And they use these sort of morphologies, sorry if you're at the back, but these hooks, that they lodge themselves into the substrate of our digestive tract. And I think that's a pretty amazing morphology, and you can find more of them if you look online. So, there we go. I'm stepping back from the disgusting side of things, and you'll all recognise this. This is the domestic cat. Oh, sorry, Francis. But it also harbours a parasite called Toxoplasma gondii. So, see, not disgusting at all. And it was discovered in a North African rodent in the early 1900s. And the primary carrier is felines, although it affects a range of warm-blooded mammals. And it has really interesting effects on behaviour, especially on rats. It increases the chances of rats being preyed upon by cats. And it does this by, rats traditionally will just avoid cats. If they smell a cat odour or cat urine, they're not going to go in that area. But rats infected by this parasite will either not notice cat smells or actually be attracted to cat smells or areas where cats are. Rats are also notoriously neophobic. They don't like new things. They'll avoid new areas, they'll be slow, they think there's danger, they'll stay put. Rats infected with this parasite will move a lot more than otherwise. They'll go to new areas. They'll increase their chance of being eaten by the primary host of this parasite, the cat. So this is a really interesting way that they manipulate the behaviour of a secondary host to be eaten by their primary host, the cat. And it's not just rats and cats, it's humans as well. So you've all heard the phrase crazy cat lady. This lady's from The Simpsons. It might not actually be entirely her fault. When we're infected with this parasite, and it ranges, so in the UK it's 22%, in New Zealand it's around 40%, in France it's around 86%. If you have a cat, or had a cat at some stage in your life, there's a pretty good chance you're infected. But it has some of these effects on us. So in the case of males, it makes us more introverted, suspicious, oblivious to others' opinions, and inclined to break the rules. So ladies, it's not always your husband's fault. Women, it makes you more outgoing, trusting, image-conscious, and rule-abiding. But it can also have big impacts on our lives. So they've looked at some car accident victims. And they found across all age groups here, if you can't see it, from 15 to 70, you're significantly more likely to be infected with toxoplasma if you cause a car accident. Maybe when you're turning at an intersection, it's just pushing you to take that extra risk or drive a bit faster like it does with rats. It also has some other effects. It makes women much more attractive to men. And it makes men act more stupid. Maybe the SPCA could use it in its next advertising drive. And toxoplasma isn't alone things that can control us. So here's another common example, rabies. When a rabid animal is about to expire, it gets sent into a rage and it goes and it bites another animal. And what happens here is the virus leaves the nervous system and enters the salivary glands. So when that animal bites another animal, it ensures that it's being transferred to a new host. My background at Victoria in science is primarily in entomology, so I feel like it would be remiss of me not to mention insects at this point. This quote is from Charles Darwin of the beagle fame. He wrote Origin of Species, and he said, "I cannot persuade myself that a beneficent and omnipotent God would have designedly created the ecumity with the express intention of feeding within the living bodies of caterpillars." So the example I've picked here is just a example of the theme of how these wasps feed on what they feed on. And the one on the left, I'm not good at Latin, is the wasp. The one on the right, beginning with T, is the caterpillar. And what happens is the female wasp will sting the caterpillar of this moth and it will lay its eggs inside it. At this point, the eggs will hatch and they'll start feeding on the caterpillar. At a certain stage in the development, they'll exit the caterpillar and they'll form these cocoons that you can see here. At this point, you'd expect the caterpillar either to leave as fast as possible or die. It doesn't do any of these things. It stays there. It's being controlled by there's up to 2 larvae inside. It's like a zombie sentinel. If everything's safe, it will just stay there. It won't eat, it won't do anything. But if a threat comes along, it will shake its head violently from side to side and do its absolute utmost to protect those cocoons. So it's a caterpillar zombie guardian, which I thought was pretty cool. And these things happen sort of in New Zealand as well. This here is the golden hunting wasp. If you're a gardener, you've probably seen it before. If you look for it, you will see it around your house. And this is just a common brown vagrant spider. And if you're a gardener, you've probably seen this behaviour before. The 2 of them will face off. They both know what's going on. And the wasp will dive in and sting the wasp, the spider, unless the spider can get away. At this point, the spider's paralysed, and the wasp will pull it back to its burrow, where it will lay its eggs inside it. The eggs will hatch and it will eat the spider from the inside out. But what's interesting is it doesn't just eat things non-discriminately. It eats the least critical organs first before it moves on, so it keeps it alive, it's like preserving its food. Before it moves on last to the brain and the nervous system. Okay, to finish, because I'll take a step back, and none of these things are disgusting. It may be that parasites led to the evolution of sex. So I've picked some classic examples here, the peacock's feathers and a bird of paradise tail feathers. They're really energetically expensive ornamentations for males to produce. And if you resist your parasites well, then you can produce this amazing plumage. But if you don't, then you're going to have droopy tail feathers, you won't have them at all. And females can see this and choose to mate with the males that best resist their parasites. Also, if you breed sexually, you're going to create a recombination of genes, so parasites can't get an evolutionary fix on you. If you reproduce asexually like some plants or bacteria, then you have the same, your offspring are genetically identical to you, so parasites can get a fix. Grooming behaviours, these are things that you'll see all the time. Sparrows and dust bars, John Preble. Outside law school, underneath the trees, there's bowls underneath the trees, and this is from generations of sparrows having dust baths and mechanically removing the parasites from their feathers. 8, grooming behaviours. You often see this in nature documentaries. They're removing parasites. Gazelles. These are gazelles' teeth. Sorry, at the back again, I wondered if it might be larger. But they're shaped like rakes. And the purpose of this isn't to eat their food, it's to remove parasites from their hide. These 2 pictures of horses, they're nuzzling each other, again, to remove parasites. Your cat at home that's constantly grooming itself, coughing up fur balls, this is an evolutionary behaviour to remove parasites. You see the same things with the lions and the plains of Africa. Population dynamics, so an even bigger scale. Once herds get to a certain size, parasites can be transferred a lot more easily between members of the herd, and it helps to regulate the size of the population. Most species are in fact parasitic. So there are around 4,000 species of warm-blooded mammal, but we've found around 5,000 species of tapeworm. And there are more being discovered all the time. There's around 200,000 species of parasitic wasps. These are the ones that I was explaining to you before. And who knows how many insects are parasitic on plants. And I wouldn't even want to guess how many fungi, plants and protozoa have parasitic life cycles. So they have really, really big impacts that you don't think about. The population dynamics, grooming behaviours, plumage, sex. And I feel like I should finish with some sort of message, so I'll awkwardly segue into it. James Lovelock, he was a scientist, he's still around, but he proposed this idea of the Gaia hypothesis. The idea is that the world's one big superorganism that keeps life on Earth conducive to life existing. I don't particularly like the idea. I think it's a bit too spiritual, but I think it has valid components. So systems don't exist in isolation. We as humans reroute ecological systems for our own ends. So we mess up nutrient cycles by adding NPK fertilizers in massive amounts to our crops. We extract and use resources and release lots and lots and lots of wastes. Modern medicine allows us to evade what might be called the Earth's immune system, so plagues and diseases. What parasites do in a body is usually they do the least amount of damage as they possibly can. And the reason for this is so that they can continue to exist and breed. If you don't breed, you go extinct. If you damage the host so much that you can't breed, it's all over. And maybe this is a lesson that we as humans can learn from parasites, just to do a little bit less damage to our host, so that indeed we can continue to persist. If you're interested in parasites, or this talk's inspired you to read more, there's a book called Parasite Rex by Carl Zimmer, which is a really interesting and accessible text. So thank you very much for having me, and for lunch. Enjoy the rest of your afternoon. In terms of pregnant women, a child's immune system hasn't evolved in vitro when it's a fetus. So pregnant women, advise, if you're pregnant yourself or your daughters are, or daughters-in-law, advise them to stay away from cat litter boxes because the parasite can be transferred through the placenta and then the baby has no way of fighting it, although the mother does. And so the mother's immune system in this particular case can't deal with it. But yeah, very valid point. No, actually, parasites have started developing resistance to the medications we have. So there are no vaccines for parasites. They're eukaryotes. They're much more related to us than, say, bacteria are. And so the traditional treatment for malaria, I don't know if I'm saying this correctly, quinine. There's malaria resistant. There's malaria that are highly resistant to quinine. And so they're actually evolving in response to our medications. So we're probably not killing them off, and they'll probably just come back stronger than before, just like bacteria. So Staphylococcus aureum, golden staph that you all hear about in hospitals, parasites evolve the same way, just at a slower timescale.